So, welcome back friends. So, we have been looking at the covariance of the Dirac equations and Lorentz transformations, and along the way I introduced you several concepts like group theory, the Lorentz group, the fact that Lorentz transformations form a group, and then I also introduced you something called the Poincare group. The Poincare group is Lorentz group plus translations essentially, and then I further then showed that the Dirac equation is covariant under Lorentz transformations if the gamma matrices transform in this particular fashion, where S is a Lorentz transformation on the Dirac spinor, essentially on the Dirac spinor. And S, we had discovered this, if S has this form, okay, then it satisfies the Lorentz transformation and it keeps the Dirac equation covariant. Okay, before going back to the Dirac solutions of the Dirac equation, and again let me mention a couple of more important points essentially. One of the things is about Poincare group. I kept mentioning that Poincare group is the one which actually sets all the representations of the particles we see in nature. So, Poincare group is group of all Lorentz group plus translations. So, that means it has rotations, boost plus translations. Now, the Poincare group, the Lorentz group itself, I will just make one particular comment saying that Lorentz group does not have unitary representations because it is non-compact due to the boost screens, whereas Poincare group can have unitary representations. Now, this is a slightly technical topic. We will need it more when we are understanding field theory, but as we will see the pathologies with the relativistic quantum mechanics or quantum mechanics in the relativistic regime, we will realize the need for a group theory, need for a full quantum field theory. In that case, it becomes important to mention that all the particles are considered to be representations of the Poincare group, and they are classified in terms of two quantum numbers, Poincare group all particles okay, are classified in terms of their spin and mass. Okay. So, there are only two quantum numbers under which you can classify all the particles, essentially the mass of the particle and the spin. Okay. So, there are two, the spin has a quantum number which essentially is given by, so there are two invariants in the Poincare group, which is essentially p mu, which is the mass square term essentially, and then this is one of the invariants, and then there is something called the Pauli-Lubansky vector, which has an eigenvalue which is m square s into s plus 1. So, this has an eigen Pauli-Lubansky vector, it is actually a pseudo vector, okay, which has a quantum number which is m square into s plus 1. So, which is essentially the spin of the particle. So, given these two informations, given the mass and the spin, you can classify all possible the representation under which the particle transforms of the Poincare group essentially, whether what is the representation okay, given a mass and spin essentially. So, with these are the two quantum numbers, whether it is a vector, scalar, tensor or so on, so you can classify depending upon the mass and spin of a particle. So, this is the point I wanted to make about Poincare group, and this is essentially important when we move from quantum mechanics to quantum field theory. Okay. So, when we move to quantum field theory, then we would need this in the classification of all particles, and then how they transform under the Poincare group, and then how to write down various invariant Lagrangians for associated with each of them essentially. Now, this sort of finishes our detour of going through all the group theory, Lorentz group and Poincare group and so on. So, okay. So, let us go back to the original question of what we started off with, okay, which is going back to few lectures before, which is the solutions of the free Dirac equation. Okay. When we left the free Dirac equation, when we are looking at the solutions of the free Dirac equation, we realized that, okay, okay. So, we looked at the so we were looking at psi 1 psi 2 solutions. So, these are the solutions we wrote down for the in the rest frame of the Dirac equation, and we gave a representation of the Dirac form essentially. So, let us start with revising this thing, and then we wrote down explicitly what is the entire form of the Dirac equation in this 4 by 4 form, and then wrote down the solutions in this particular fashion. So, for any in a static frame, we wrote down the solutions in this particular fashion. Okay, in the static frame. Now, for a non static frames, essentially for any frame in general relative frame, we can write down the equations as follows. So, this detour was essentially to get to understand the question, what is a spinor? So, what is a spinor, and what has it had to do with Lorentz transformations? So, this was the reason, because what we saw was each component of the Dirac spinor satisfies the Schrodinger equation. So, the solutions of free Dirac particles, or we can say it as wave functions, because remember that we are still in relativistic regime and we are doing quantum mechanics essentially. So, the solutions can be written in this particular fashion. So, they are psi p plus minus x and t, x stands for x and x bar and everything. Okay, and n is some, okay, I think I should use a curly n. Some normalization factor e power I p dot x let me write it down neatly, minus plus E t. Now, I introduce u and v, you can also say chi and eta essentially. Okay. Now, what is this thing essentially, that this plus stands for positive energy solutions, negative stands for negative energy solutions. Now just to bring you back into the picture, essentially that we found that when we, I think you must have in the detour we must have forgotten what are the solutions of the Dirac equation. The Dirac equation has solutions again positive and negative energy solutions. These are 4 component spinors, so psi 1, psi 2, psi 3, psi 4. What we wrote down were essentially psi 1, psi 2, psi 3 and psi 4. We wrote it down then. Now what I did was I wrote the upper 2 components separately and the lower 2 components separately, because the upper 2 components I consider them to be positive energy states and the lower 2 components I consider them to be negative energy states essentially. So so we can write we can write okay. So this psi 1, psi 2, psi 3, psi 4 can be expressed in terms of chi and eta. Okay. So chi and eta. Okay, let us substitute the positive energy solutions first essentially. So chi eta E times chi eta e power I minus I p x p bar dot x is equal to m minus I sigma dot delta bar nabla minus I bar des minus m chi eta e power minus I p dot x. So what we have is that, so we have this, let us consider the upper 2 components as chi and the lower 2 components. Okay, if you want, what I did was go back to these solutions. These are your static solutions, okay, your static solutions, and before that you have this equation. So this is the equation which you started with essentially. This del 0 is your E, nothing but your E. E is nothing but I del by del t. You can write it in terms of E t essentially, or E in momentum space essentially. Okay. So you can these are position space wave functions. So what we are looking at are momentum space wave functions. So this just becomes, okay, one second, before you consider that I have jumped a lot. So this in momentum space becomes chi is equal to m chi plus sigma dot p eta, because momentum p bar is equal to I minus h del and E is equal to I del 0. Okay, in momentum space E and P have these definitions essentially, and then you have E eta is equal to sigma dot p chi minus m dot eta. Now what I did was nothing, this just I wrote psi 1 psi 2 in terms of chi and did the same thing in momentum space essentially. Now this, now if you want okay, now if these solutions have to have a positive meaning any non-zero solution, this determinant of the matrix should be 0 essentially, the determinant of the matrix. So this gives me sigma dot p, okay, and you can write it again in terms of the same matrix. This is sigma dot p, okay, this gives me sigma dot p square, which is nothing but p square. So this essentially gives me the condition sigma dot p is equal to nothing but p square. So, knowing this condition, so this gives me back my relativistic equation E square is equal to p square plus m square. Okay. So, from the momentum space we end up having the same relation as in the same dispersion relation as for the Klein-Gordon equation essentially. So, the Dirac equation just gives you the same equation as the Klein-Gordon equation. Now, the point is now let us take these two. These are the two important relations which you will need. Okay, these are the two important relations. Okay. Now, these two relations, now you can see that I can use the second relation. So, these are first relation and this is second relation. Now, the second relation can be used to re-express first. Okay. So, you can solve for say eta and express chi in terms of the eta, or express eta in terms of chi. Say for example, you can bring E plus m on the right hand side because it is eta, and then eta becomes sigma dot p chi by E plus m. So, this is what it is. So, using the above two relations, in momentum space we have eta is equal to sigma dot p by E plus m chi. Okay. Now, you can put it back into that relation essentially. Okay. Okay. Now, you can say that what is my ask the question, what is my positive energy solution, what is my negative energy solutions, and so on. So, okay. So, you can actually derive the condition from this essentially, that an arbitrary two component spinor. Now, if you given this arbitrary two component spinor, put it back into your Dirac equation, the solutions above, essentially putting it back into this above solution for eta by eta essentially. So, you can derive a complete condition in terms of chi essentially. So, in terms of chi. So, before that let us do normalization. So, the normalization assuming some box or volume such that psi dagger psi okay, x cube, essentially psi of x cube is equal to 1, and chi dagger chi is equal to 1, assuming these two. So, you end up having taking psi is equal to this relation essentially, that this is 1 plus p square. You can solve for psi is equal to, what is psi? Psi is nothing but your this thing, whatever you have written here, this is your psi. Now, take positive energy solutions, substitute wherever there is eta in terms of chi, and you will have some NP, some because we want to derive this normalization factor, eta whatever we call it as n cap, using the same notation, n square L cube chi dagger 1 plus p square by E plus m square times chi. Now chi is some arbitrary spinor that is 0 1 1 0, essentially it's normalized spinor. Okay, that's what we have chosen. Okay, with this, okay, now you can solve this relation. So this relation would be n square L cube, okay, into is equal to times 2e by E plus m. With this you get the normalization factor would be square root of E plus m by 2e. There is a L cube factor. Now you can take okay, you can take okay. Now with this normalization factor, okay, you can define in terms of the positive energy Dirac spinor, which is defined to be, one can define positive energy spinor. This fixes everything for you. So this okay, this the normalization fixes everything for you. With this you can define what is U as follows. Define the positive energy spinor U of P s is equal to root of E plus m 1 sigma dot P by E plus m chi of S. Now you have to be careful with this. This is S here. Let's understand this notation a little bit more. Now S is two component. Okay. Now sigma dot P is again what we have seen is Px, Py, Pz and everything. It's a 2 by 2 form essentially. Okay, it's a 2 by 2 form, and 1 is again this entire thing. Now what is chi? Chi S is, it has spin half. Spin half is equal to 1 0. Spin minus half is equal to 0 1. Okay. So what we have discovered is the positive energy solutions of, I didn't write down the full energy solution because the full wave function are given in terms of, you can express them in this particular fashion in terms of the two component spinors with some normalization factors and multiplied by an arbitrary two component spinor which is 0 1 1 0 essentially for spin up spin and down spin. It has two components, the momentum and the spin. So it has 1 0 0 1 times at the bottom, this is a full 4 component thing, 4 component. So this is a full, makes it full component. So this is chi s multiplying 1 on the top and chi s multiplying sigma dot P times E plus m at the bottom, and each chi s has two solutions, which is S is equal to plus half, S is equal to minus half. So which is 1 0 and 0 1 with this particular thing. So U of P bar S is a 4 component positive energy solutions spinor, one for the up type spin, one for the down type spin, okay, or one for spin half and one for spin minus half essentially. Okay, now this point is clear, right? This is exactly like this is the most general momentum state solutions. momentum space solutions for the Dirac equation. Okay. This all starts with this equation. So, we have just decomposed this equation, we already started off earlier. So, this is started earlier, essentially we just wrote down the Dirac equation in the momentum space and derived the solution. So, the derivation of the solution is very simple. You just have to identify the second component is equivalent to the first component by this relation, putting it back, deriving the normalization and giving you back this particular thing. So, now the full positive energy solutions in terms of wave functions in terms of x will drop the L cube at some point essentially. This is in the full glory what is u, the wave functions, because u is just the spinor and the wave function contains the e power IPX form also essentially the way. Okay. The wave function contains the normalization factor as well as the e power IPX. Now, you can do the same exercise for negative energy solutions. Negative energy solutions we have to see them essentially. So, these are called V. In this case we start with the same equations, but E becomes minus E. We start with the same equations, but E becomes minus E, because this is the same thing which we had from the I del 0 essentially, the same thing which we had under this particular, oh god, we had to go really up when we expanded this. So, there was two components with positive and two components with minus I del 0 essentially. So, we notice that essentially. So, these are the two things with minus I del 0. Oh. So, in this case you have minus E chi is equal to m chi plus sigma bar dot p bar eta minus E eta is equal to sigma bar dot p chi minus m eta. Now, here too we have the same relations, we can use the same thing, but we can now start with chi is equal to minus sigma dot p by E plus m eta. Chi is equal to minus sigma bar, this is obvious from the above relation essentially. So, you have chi is equal to minus sigma bar p by E plus m. Okay, you get this one using the first relation. Considering the first relation. Now, you put it back in 2, okay, you end up having similar normalization factors and everything, but in the opposite end essentially. For this we will introduce another two component spinor. Let us use the same, okay, instead of the same two component spinor we can use another two component spinor. Okay. What we will do is we will see that e power minus s is equal to minus I sigma 2 chi of s. Okay, let's choose. Okay, this will become easier once we know why we are choosing this a bit later essentially. Okay, because this is a very nice choice of the things. Okay, now you choose the spins. This chi is the same chi as before, essentially chi dagger chi is equal to 1, 2 component spinner. Okay, so these are the phases we choose essentially. This eta is not this phase, this eta essentially. So this is okay. This eta is the same as this eta in the sense that eta minus half is equal to minus I sigma 2 chi plus half that is equal to 0 plus 1. So it is inverts the one of the previous eta plus half is equal to I sigma 2 chi minus half that is equal to minus 1 0. With this you can define V, which is the antiparticle spinor, Vf as is equal to root of E plus m sigma dot p bar E plus m 1 minus I sigma 2 chi of s. Okay, so this is your negative energy solutions. So see that the spinors are different, U and V spinors are different. They give you different dispersion relations because they have different sign of energy. Okay, but most of the other factors are same essentially, and the wave function, except that they are okay, except that they are in the upper and down part essentially minus p psi of minus x, negative values of x minus negative energies of x is equal to root of E plus m sigma bar dot p bar by E plus m times 1 V of Ps e power minus I p dot x plus I p dot x, sorry, this is plus. So this is the important relation, second set of relations. These are the wave functions for the negative energy solutions. These are the wave functions for negative energy solutions. There are two main things that you will see immediately, that these the wave functions which you introduced u and v are orthogonal to each other. U and v are orthogonal to each other, and we'll also okay, these are okay. So that means V dagger or V bar minus P S prime U of P S is equal to delta. Now we can make it much more this PP prime delta SS prime. Okay, no, let me just make it whatever it is. In general, whatever it is, this and is equal to u dagger, okay, p dot s, now v of minus p s prime, any of them essentially, whatever combination you take, the wave functions u and v are orthogonal to each other. So their spinors cancel each other and they lead to 0 essentially. Okay. Okay. Then we also have the completeness relationships and other things. We will see the auto products. Okay. So, okay, okay. So let's just summarize. Essentially, what we had tried to look at is momentum space wave solutions for free Dirac particles. Momentum space solutions for the Dirac particle, where we introduce u and v fields, u and v wave functions for the first time. What we did, how we did was essentially to introduce just write down the Dirac equation in the momentum wave equation form. So we started off with writing in this particular fashion, where I identified I minus I del with the p and e with the I del 0, and then we get up and u, the main crucial point is that psi itself is written in terms of some chi and eta, two component spinors. The moment you write it in terms of two component spinors, the weak equation just decouples into one component, two 2 by 2 forms essentially. So chi and eta are two component spinors. So these two component spinors, now you put it now you see, now you can, if you consider positive energy state solutions, essentially now you have only positive sign for the energy, and now you can put back using equation 2 into 1, you can put back equation 2 into 1, and this gives you this nice relation for this for the normalization, and from there you can define, somehow this thing is not moving, using the normalization you can derive this normalization, and the moment you have the normalization, now you can define the positive energy spinor as using an arbitrary spinor chi, as another two component arbitrary spinor chi, as follows essentially, that you have the upper component given by chi and the lower component given by sigma dot p, the normalization whatever we have derived essentially. Now which is nothing but the second component which is eta. So we have substituted for eta here essentially, and this is just all positive energy solutions. Now the total the u spinor is a positive energy spinor, and it's 4 component, and you have seen we can write it in this particular fashion. Now you do the same thing with negative energy solutions, and you end up having this particular form for this thing. This is the negative energy v vector, negative energy v vector, and what we see is that u and v are orthogonal to each other, and this is one of the first properties which we will see. We will see further properties in the next class essentially. So we will see u bar is equal to what, and what we have written just to show in terms of dagger. I will introduce bars and everything in this in the coming class, and you will see what is u bar and u bar u in terms of the normalization factors and completeness relations. And once you do that, you are sort of know all the properties of the positive energy solutions and negative energy solutions, and you will be ready for some calculations essentially. Okay, so I'll stop here. Thank you very much, and you're welcome.